A Huawei Ascend 910B accelerator card sits on the bench. It is a full-length, full-height PCIe board, roughly the dimensions of a hardback book, pulled from a domestic Chinese artificial intelligence cluster sometime in 2023, after export controls made the Nvidia A100 unreachable for that market. The surface presents exactly what any high-end accelerator presents: black printed circuit board, passive heatsink fins running the length of the card, dual high-density power connectors, and a row of ports at the bracket end. The deepest layer does not present anything like that. It presents a system that was redesigned from the inside out in every layer simultaneously, because the constraint placed on its procurement environment became the engineering specification for its internals. The surface suggests competitive hardware positioned against an Nvidia part. The deepest layer reveals something structurally different, an object whose architecture, whose memory configuration, whose interconnect ownership, and whose software library were all determined not by what a design team would have chosen freely, but by what remained available after the procurement environment was closed. That is not a backstory for this card. It is visible in the silicon, legible in the compiler, and measurable in the bandwidth figure. We will open this card cut by cut, board, and interconnect first, then the processor package and its die, then the memory stack mounted beside it, then the die architecture and its on-chip hierarchy, then the interconnect fabric in depth, and finally the software layer that binds the whole object together, because that last layer is where the constraint becomes a text that can be read directly. The outermost layer of the Ascend 910B is its board and interconnect configuration, and that layer carries the first diagnostic signal before a single component is identified. The card draws roughly 400 watts at peak, per Huawei's own published specification, and the passive cooler spanning its length was designed for forced air rack environments rather than open-air benches. Dual power connectors supply the draw. At the bracket end, the card exposes ports for Huawei's proprietary coherence fabric, called the Huawei Cache Coherence System, used to link multiple cards within a single server node. Independent teardown observations circulating in the hardware analysis community are consistent with this layout and with the bracket port configuration. Those coherence fabric ports at the bracket are not a performance feature. A card designed to drop into an existing high-speed interconnect ecosystem built around a dominant supplier's fabric would not carry its own coherence ports at the bracket. It would rely on the external fabric already present in the system. The presence of a proprietary fabric here encodes the first structural fact about this card's origin. It could not assume any external high-speed interconnect would be available or licensable. The outer shell already expresses the supply chain isolation. The spec sheet lists the fabric's bandwidth. It does not state that the bandwidth exists because the alternative was foreclosed. One layer beneath the heatsink sits the Ascend 910B die itself, and this is where the fabrication tier enters the record. Huawei and its fabrication partner describe the process as a 7-nanometer-class node. Independent analysts who have examined process-level evidence note that this designation does not map directly onto the leading foundry's 7-nanometer generation in transistor density or performance per watt. The two nodes share a marketing tier designation and diverge in almost every physical parameter that determines how much compute fits in a given area and how much power it consumes doing it. The die is large. Teardown imagery shared by hardware researchers places it among the larger monolithic dies in production at that facility. The die is large because the process node is not at the leading edge. When a fabrication process cannot pack transistors as densely as a 4-nanometer or 3-nanometer node, recovering the compute density required for competitive inference performance requires physical area. The transistor count that a design team targets to achieve useful throughput for large model workloads has to fit somewhere on the reticle, and at this process tier it fits by expanding the die footprint. Expanding die area increases yield risk, because a larger die on a given wafer is more likely to contain a defect that renders it unusable. It raises power draw per unit of compute, because more transistors running at this process node's leakage characteristics consume more power than the same count would consume at a denser node. It constrains the aggregate memory bandwidth the die can address, because the number of high bandwidth memory interface connections the package can support is bounded partly by the physical dimensions of the die edge. Every one of those downstream effects appears in the layers below this one. The fabrication restriction is not a caveat appended to the card specification. It is the reason the die is the size it is, and it propagates through every subsequent layer of the object. Huawei's own figure for peak 16-bit floating point throughput on the 910B sits in the range of 256 to 320 terafloating point operations per second depending on configuration. That is the company's own claim, and no independent benchmark has confirmed that the card sustains throughput at that level under representative large model training or inference workloads. The distance between a peak specification and a sustained measured figure is not small for any accelerator. For this card, the size of that distance is unknown outside Huawei's own data centers. Mounted beside the compute die is the card's high bandwidth memory stack, and this layer carries the upstream dependency that governs real-world throughput more directly than the compute specification does. Huawei claims 64 gigabytes of capacity and peak aggregate bandwidth in the range of roughly 800 to 900 gigabytes per second. For a concrete reference point using independently confirmed figures, the Nvidia H100 in its highest bandwidth configuration carries 80 gigabytes of high bandwidth memory at roughly 3.35 terabytes per second, a figure sourced from Nvidia's own disclosed specifications. The bandwidth gap between these two objects is the single largest measurable distance between them as compute platforms, and it has a procurement dimension that does not appear anywhere in the specification table. Sourcing high bandwidth memory at the volume and the specification tier that the leading artificial intelligence accelerator supply chain accesses requires suppliers not subject to United States export controls, and that list is short. The tier down suggests that the memory configuration on this card reflects what was procurable under tightening restrictions, not what an unconstrained design team would have selected as the optimum for this die's compute capability. The capacity and bandwidth figures Huawei claims are real in isolation. What they do not state is that the configuration encodes a supply chain decision as a physical object. Memory bandwidth is the governing constraint for large model inference. A transformer moving attention weights and activation matrices through a forward pass is almost always bandwidth limited rather than compute limited. The bandwidth ceiling on this card therefore sets the effective ceiling on the scale of model the card can serve at low latency, and it sets that ceiling below what the compute arrays could theoretically sustain if memory could feed them faster. To render the gap as a physical quantity rather than a ratio, the bandwidth distance between this card and the leading Nvidia part is roughly the difference between a water main and a garden hose when you are filling the same tank on a fixed schedule. The compute die can request data faster than this memory stack can deliver it, and everything downstream of this layer is shaped by that fact. The layer below the memory configuration is the die architecture itself, and here the design response to the bandwidth gap becomes visible in the structure of the silicon. The Ascend 910B implements Huawei's DaVinci architecture, organized around compute cores called AI core units, each of which carries local instruction buffers, multiply accumulate arrays, and a dedicated on-chip scratchpad called the Level 1 buffer. This architecture is documented in Huawei's published technical white papers and corroborated by compiler-level analysis from developers who have worked directly with the Ascend stack. The on-chip memory hierarchy is structured to keep frequently reused tensor data close to the compute arrays, reducing the number of times a computation must reach out to off-chip memory to retrieve data it has already fetched. This scratchpad architecture is an explicit engineering response to the bandwidth gap identified in the layer above it. When external memory cannot deliver data fast enough to keep the compute arrays occupied, the design moves more data management inside the die and gives the compiler, or the programmer working below the compiler, explicit control over what lives in that scratchpad and for how long. This architectural pattern predates the general-purpose graphics processor compute model by decades. It reappears here because the circumstances that originally motivated it have reappeared. Constrained off-chip bandwidth forces a design to be deliberate about data residency in a way that abundant bandwidth does not require. The architectural choice visible in this layer is not a competitive differentiator selected to distinguish Huawei's product from its competitors. It is the shape that the bandwidth constraint imposes on the inside of the die, and it has direct consequences for the software layer below it. The interconnect fabric visible at the bracket in the outermost layer extends deeper into the node architecture. and examining it at this depth exposes the vertical integration decision it represents. The Huawei cache coherence system connects multiple 910B cards within a single server node, forming a cache coherent domain across the accelerators in that node. Huawei's Atlas 900 artificial intelligence cluster, built from nodes populated with 910B cards, is described in company materials as achieving aggregate throughput competitive with large-scale accelerator clusters for certain training workloads. That is a company claim for the cluster as a system, not an independently verified per-card figure, and no open literature source as of mid-2025 provides independent confirmation of sustained latency and bandwidth under real distributed training traffic across this fabric. A proprietary cache coherent fabric at this level of the stack requires Huawei to own every component in the communication path. The silicon implementing the protocol, the firmware managing it, the topology driver controlling how cards discover each other, and the cluster scheduler that allocates communication resources across a training job. That is a substantial engineering burden, and it is a burden that adds development cost and maintenance complexity to every generation of the product. The reason this burden is carried is that the alternative, licensing, or depending on an interconnect standard maintained and controlled by a supplier subject to export control regimes, was foreclosed by the same restrictions that constrained the fabrication node choice. The Huawei cache coherence system is not a product differentiation decision. It is a vertical integration decision made because horizontal integration was unavailable. Every bracket port on this card is the physical expression of that unavailability. The deepest layer of the Ascend 910B is not silicon. It is software, specifically the compute architecture for neural networks, Huawei's operator library and graph compilation framework that sits between a user's model and the Ascend hardware. This framework is documented in Huawei's developer portal and has been examined publicly by developers migrating PyTorch and Mindspore workloads to the Ascend platform. The framework exposes operator fusion, memory planning, and tiling decisions that correspond directly to the DaVinci Core's scratchpad architecture and to the high bandwidth memory bandwidth ceiling established 2 layers above. This is where the anatomist's own reading departs most sharply from anything on the specification sheet. The compute architecture for Neural Networks Operator Library is not a translation layer placed on top of a general-purpose architecture to make it compatible with frameworks written for another platform. It is a set of pre-computed answers to the memory management questions that the on-chip scratchpad forces the system to answer explicitly. Each fused operator in the library encodes the correct tile size for the AI core's local buffer depth, the correct prefetch pattern for the card's high bandwidth memory bandwidth ceiling, and the correct data layout for the specific memory hierarchy this die implements. Those parameters are not chosen from a menu of reasonable options. They are what they are because the hardware parameters are what they are, and the hardware parameters are what they are because the procurement environment was what it was. The binding between this software and this hardware becomes concrete when a single tensor operation is traced through the stack. A matrix multiply in a transformer attention block arrives at the compilation framework as a graph node. The framework matches it to a fused operator in the library. That operator tiles the computation to fit the AI core's local buffer at the depth this specific die carries. The tiled computation is then scheduled to overlap with a high bandwidth memory prefetch that is sized in time to account for the card's bandwidth ceiling, not a generic bandwidth assumption, but this card's specific figure. The prefetch data lands on the multiply accumulate arrays as a precisely sized block whose dimensions were chosen to keep the arrays occupied through the latency of the next fetch. The prefetch schedule is not a general purpose optimization. It is the schedule that this bandwidth figure makes necessary, and it would be wrong for a card with different bandwidth, a tensor operation that a programmer familiar with the dominant compute platform writes once, and that platform's compiler handles generically across a range of hardware generations, must on this stack either be matched to the operator library or hand-tuned to the tile geometry of this specific die. That is not a deficiency in the library. It is the structural consequence of a software layer grown inside a hardware constraint rather than layered on top of a general-purpose architecture. The software works because it was written to make this specific hardware usable. It is not portable in the way that software written for an abstracted hardware model is portable, because the hardware it addresses is not an abstracted general-purpose target. It is a specific object shaped by a specific procurement environment and the software is the record of that shape expressed in operator entries and tile dimension constants. The restriction that prevented access to leading-edge fabrication capacity and to the dominant interconnect ecosystem did not produce a hardware void. It produced a hardware target with specific, non-optimal parameters, a die area set by the process node gap, a memory bandwidth set by what was procurable, an interconnect owned entirely in-house because the alternative was unavailable. The compute architecture for neural networks is the record of those parameters written in software. Cut to this depth, and the buried constraint is fully exposed. The export restriction is not the backstory of this card. It is the engineering specification of this card, present at every layer, from the bracket ports to the compiler library entries. Three things this dissection cannot settle deserve explicit statement. The first is the performance claim. Every throughput figure cited for the Ascend 910B that originates with Huawei is the company's own figure. No independent benchmark has confirmed that the card sustains those figures under representative large model training or inference workloads in conditions outside Huawei's own infrastructure. The distance between peak specification and sustained measured throughput under real workloads is the unknown that most matters for procurement decisions, and it remains unknown from external evidence. The second is the process node gap. The 7-nanometer-class designation is Huawei's and its fabrication partners' own description of their process. Independent process analysis by semiconductor research firms suggests meaningful differences in transistor density and leakage characteristics compared to the leading foundry's generation of the same nominal tier. The magnitude of the performance and efficiency gap implied by those physical differences cannot be settled from teardown imagery or published specifications alone. The third is thermal and reliability behavior at sustained load. Die area at this process tier correlates with higher power density, and the passive cooler design and power budget specify a controlled data center environment as the operating context. Whether the card sustains its rated performance at the thermal limits of dense rack deployment across the operational lifetime that enterprise customers require is not visible in the silicon and has not been reported with independent instrumentation in the open literature. What the dissection can settle is structural. Every layer of this card, die size, memory bandwidth, interconnect ownership, software coupling, is consistent with a system designed under hard procurement constraints, and those constraints are traceable in the object regardless of whether any particular performance claim is confirmed. This card does not refute the proposition that export controls created meaningful friction for Chinese artificial intelligence hardware development. It demonstrates something more specific, and structurally more significant, that the controls shaped the development rather than halted it, and that the shape is now a fixed characteristic of the object and of everything downstream of it. A system built under hard procurement constraints and a system built without them are not the same system running at different speeds. They are different systems, with different internal architectures, different software contracts, different upgrade paths, and different ecosystems of models optimized to run on them. The Ascend 910B is not a slower H100. It is an object that reflects the specific environment in which it had to exist, expressed in die area and bandwidth figures and compiler library entries that were not chosen freely. What this card proves, cut by cut, is that a closed door does not produce nothing. It produces a different floor plan. That is one card, opened. There is a memory controller, a network switch, a compiler toolchain, a power management integrated circuit, each of them an object with its own layered structure, each of them shaped by the same procurement environment that shaped this one. Tell us in the comments which object you would put on the table next. If this kind of dissection is useful to you, subscribe and turn on notifications so you are there when the next object is opened.